Hello everyone, this is topic 5, 6, and 7 for exam 4. This is part 2. Last time we went over these notes where we were exposed to the P series, so very the form 1 over n to the P, converges if P is greater than 1, diverges if P is less than or equal to 1, so very simple series. And then we started talking about comparison tests, and in particular the direct comparison test. Just a couple things to note. It's very important that you understand that these are the inequalities that must be established to use the direct comparison test, and we want to do so in general. Once we establish which way the inequality points, that dictates which part of this theorem we're using, either the convergent case, what I like to call a convergent case, or the divergent case. So what we will be comparing to often is either a P series, so 1 over n to the P again, there's an example, or a geometric series. Remember, there's two forms for the geometric, index starting at 1 or the index starting at 0, but basically they both can be recognized by a real number, typically a fraction, doesn't always have to be, but usually is raised to a variable power. So that's when you want to think geometric. So we did see an example, and with the example, you want to make sure that you take advantage of the table that we've been talking about that's has all of our tests for series, and this you're allowed to write anything you want on the back of this paper and bring it into the final exam with you. But note that under the comparison cluster, the first two letters I and II are the direct comparison, and the third one is the limit comparison that we'll get to next video lecture. But keep in mind again about the direct comparison, it's this inequality that dictates which case we're using. So we saw an example last time where when we established that inequality, it was the convergent case because it was less than, so look at the table, it says less than, and we were able to prove convergence of that series. So here's a similar series, but the first thing you might want to do is get rid of the radicals, so the sum is then goes from 2 to infinity of 1 over n to the 1/2, of course, minus 1, and then we'll call that the sum of the a sub n. Because remember, the sum of the a sub n is the given series. And then we have to choose a comparison series. And our comparison series is usually found by just eliminating one extra term in the denominator. If we get rid of this negative 1, we have 1 over n to the 1/2, which is a P series. So very similar to this last example where we eliminated this positive 1 in the denominator, and we had 1 over n squared, which was our comparison series. So that's our plan, and we're going to call the sum of the b sub n the comparison series, and that'll be the sum as n goes from 2 to infinity of 1 over n to the 1/2. Okay, now the most important thing, once again, is establish this term-by-term comparison between a sub n and b sub n. So the structure of the solution, as before, write down a sub n, leave a space for the inequality, write down b sub n. You can literally write down their nth terms right underneath. 1 over, I'll use the n to the 1/2 minus 1 version, and the 1 over n to the 1/2 for the b sub n. And then determine which way the inequality points. Remember, you can, it's not cheating, but some people will just literally plug in a value of n, a number, and see which way it points. Like for example, since we're dealing with square roots, you might choose 4 because that's a perfect square. So if you have 1 over 4 to the 1/2 minus 1, or 1 over 4 to the 1/2, that would be square root of 4 is 2 minus 1 is 1, so 1 over 1 is 1. This would be 1/2, and then you can see that 1 is bigger than 1/2. So it's not really cheating, but it's not really doing it in general. The general way to prove which way the inequality points, as we discussed when we talked about this first example last lecture, is to take advantage of the reciprocal relationship of inequalities. That is, if you have two numbers, you're comparing two numbers, like let's say 2 and 4. Obviously 2 is less than 4. But if you take the reciprocals, 1/2 and 1/4, 1/2 is 0.5, 1/4 0.25, and the sense of the inequality reverses. So that argument can be used in this case by just saying that this denominator is less than, and will always be, no matter what the value of n is, this denominator on the left is always going to be less than the denominator on the right. So therefore, its reciprocal will be greater than. Okay, so then once you've established the inequality, you go to your table, you look under the comparison cluster, and which way does it point? In this case, we have greater than, so it's case II, second case. This tells us we're going to be using case II. And I even like to go so far as to say what case it is. Like, is it the case that proves convergence, or is it the case that proves divergence? And that's the divergent case. So now all that we need to show is that the sum of the b sub n diverges. And then by the theorem, we could state that our series diverges as well. Now the sum of the b sub n was the sum as n goes from 2 to infinity of 1 over n to the 1/2. And you might argue, okay, it's not exactly a p series because it's not starting at 1. But the argument there would be that if it did start at 1, that first term would be 1 over 1 to the 1/2, or 1. So that finite number 1, if we were to start at 1, is not going to affect the convergence or the divergence of this series. Because if it converges and we started at 1, then it would just converge to a bigger number, 1 bigger. And if it diverged, then the 1 wouldn't matter because it's going to diverge anyway. So therefore, the index is okay. We can almost ignore that. But at this point, you have to tell me what type of series you're dealing with. And it's a p series. Tell me what the value of p is. In this case, it's 1/2. And look at your table if you need to. Under the p series. See, that's the third row down here. If p is less than or equal to 1, it diverges. So you have to tell me type of series, and what determines convergence or divergence, and then obviously tell me it diverges. Okay, but that's not enough. We're pretty much done, but this might seem trivial, but it's not. You have to say by the theorem that the original series sum of the a sub n, which was sum as n goes from 2 to infinity of 1 over, I'll use the square root of n minus 1, that this also diverges. And the reason why that statement is necessary is because in the theorem, it's these two things that determine divergence in this case. The fact that we have a series that we've proven has terms that are greater than the comparison series. And if the comparison series diverges, which we had proven, then our series being bigger than that series would also have to diverge. So that's a necessary statement. Okay, so we'll get to the last two examples of direct comparison. I'm basically giving you one of each type. So a p converges, a p diverges, and let's see here. Whenever you see a real numbered base raised to a variable power, that's when you want to think geometric. And that's what we see here, is these bases raised to the same variable power. And what we could do is, well, we're going to consider that to be the sum of the a sub n. So that's the given series. And we're going to make a comparison to what we're going to call the sum of the b sub n. But what we do is pretty much the same thing as the previous examples, where we knock out that extra plus 1 that's in the denominator, and we have 2 to the n over 3 to the n. So the sum is then goes from 0 to infinity of 2 to the nth over 3 to the nth. And then we're going to geometricize that series. Because you might not think it's geometric at this point, but consider this. The basic rule of algebra for, let's say, a quotient raised to a power, x over y to the nth. That's the same as x to the nth over y to the nth. So therefore, we're going to use this rule in reverse, and we're going to consider that we have 2 to the nth over 3 to the nth, and reversing the rule, it's different bases, but the same variable power. We could express it as 2/3 raised to the nth power. And so if we take the time to show that, then this is now in standard geometric form. So that's a little trick there. All right, and then from here, it should be pretty routine. You're going to make the comparison, a sub n to b sub n, write down the terms directly underneath, 2 to the nth over 3 to the nth plus 1, 2 to the nth over 3 to the nth. You can plug in numbers, like I mentioned earlier, but I'm going to use the argument, the general argument, that in this case, and it's probably best to use this ungeometricized form for b sub n, because that way you can show this direct term-by-term comparison easily. The argument would be that the numerators are the same, so therefore they will not affect the sense of the inequality. But when we compare the denominators, this denominator on the left is always going to be larger than this denominator on the right. So in terms of their reciprocal, it would be smaller. Okay? So if you want to plug in a 2 for n or a 3 for n and crunch down the numbers and see which way the inequality points, feel free to do so. But I'm going to argue the general way. Okay, so then go to your table. Once you set up that inequality, go to the table, look at the tests. Which one is it? When a sub n is less than or equal to b sub n, it's case I. So this is case I. And again, I'm even going to go so far as to say that that's the convergent case. Because that helps me remember what I need to do now. If the theorem's going to work, now I need to show that the sum of the b sub n converges. And the sum of the b sub n was the sum as n goes from 0 to infinity of 2/3 to the nth. Alright, now compare that to your standard geometric forms. In particular, this one, we've got a starting index of 0. So the power on the common ratio, r, should be n, and it is. So therefore, we can state that this is a geometric series. And what determines convergence or divergence, if you have to go back to look at your table, under geometric series, it's the absolute value of r. If it's less than 1, it converges. Greater than 1, or equal to 1, it diverges. And here's the two forms again, starting at 0, n is the power, starting at 1, n minus 1 is the power. So it's the absolute value of r that dictates convergence or divergence. I'm going to add the term series here. So it's a geometric series. Okay, the absolute value of r is the absolute value of just matching it up. The r is the fraction, it's in parentheses, 2/3, which is 2/3. And when r is less than 1, then it converges. Okay, so now finishing it up, you have to make that final statement once again by the theorem. You could say by the direct comparison test, whatever you wish. The original series, the sum of the a sub n, which was the sum as n goes from 0 to infinity of 2 to the nth over 3 to the nth plus 1, that this also converges. Okay, so one last example for the direct comparison test here. Similar to the last with respect to the fact that we have the real numbers raised to variable powers. So we're going to call it the sum of the a sub n. And we're going to compare it to, we're going to call the sum of the b sub n. And it's going to be equal to the sum as n goes from 1 to infinity of, okay, once again, we're going to knock out this negative 0.9 that's in the denominator. Initially, rewrite this as 7 to the n minus 1th over 6 to the n minus 1th. But then using that rule that we talked about in the last example, that little algebra rule in reverse about powers, got different bases but same variable power. So we could write this as a sum as n goes from 1 to infinity of 7/6 to the common variable power of n minus 1. And now it's in a standard geometric form. Okay, so now the direct term by term comparison. So here's my a sub n space b sub n, literal length terms, 7 to the n minus 1th over 6 to the n minus 1th minus 0.9, and use the ungeometricized form for b sub n, because again the argument can be made that the numerators are the same, so that will not affect the sense of the inequality, but this denominator on the left is always smaller than the denominator on the right because we're subtracting 0.9 every time. So this one's denominator is always smaller than this denominator, so therefore the reciprocal is going to be greater. Okay, so then at that point, you go to your table once again, look under the direct comparison cluster, a sub n is greater than b sub n, that's case II. Okay? So, this is case II. And once again, we'll go so far as to say that that's the divergent case. Okay, so now all we need to do is show that the sum of the b sub n diverges, and if it does, then together with what we've previously established, we'd be able to say that our series diverges. So the sum of the b sub n, sum as n goes from 1 to infinity, use the form, the geometric form, 7/6 as a quantity to the n minus 1th. Make sure it matches with the standard geometric form. If n starts at 1, the form should be ar to the n minus 1th, and it is. So then you have to tell me what type of series we're dealing with. And again, it's a geometric series. Tell me what determines its convergence or divergence, which is the absolute value of r. In this case, the absolute value of 7/6, which is 7/6. And 7/6 is greater than or equal to 1. If you have to go to your table at this point and look under the geometric series criteria for convergence or divergence, r is less than 1, absolute value, that is, it converges, and if r is greater than or equal to 1, it diverges. So it's greater than or equal to 1, so therefore we could say that it diverges. And finally, by the theorem, because again, with regards to this final statement, it's the two things taken together that prove divergence. Okay, the fact that we've proven we have a series that has terms that are greater than a series, our comparison series, which we've proven to diverge. So if our series is bigger, our series would diverge as well. So therefore, by the theorem, we'll say the sum of the A sub n. I always like to recopy. That this diverges as well. Okay, so I think we'll stop right there. We've got topic 7, which is in the same packet, and it's the limit comparison test. So I think we'll stop right here and do that in a third part. So we'll see you when you're ready.